This is part of new thermodynamics, and we're going to consider boiling and lost work in simpler terms. I did a video earlier that was in a little more complex terms, and I'm going to try to simplify it a bit so that people can understand the fundamentals. Consider work and potential energy. Okay, work is the dot product of force times distance. Now this man in the picture here, he's lifting a weight. Okay, and it's actually the force times the change in elevation in this case. So work in his case is equal to the mass times the gravitation, null constant, times the change in height, which is dh. Okay, and g is 9.82 meters per second squared. Okay, fine. And this is also equal to the potential energy change. Right? Now, we can also apply the same principle to a cylinder of gas that's expanding by a height of dh. It's got to lift up the atmosphere's mass above it, because you can imagine the atmosphere is putting pressure onto it, and that's really from the weight of the atmosphere. Okay? And so basically, in terms of the area of the piston head, okay, which is vertical to the page here, it is force over area times area, the dot product of area and the height change, and this is equal to pressure times dV, right? Force over area is pressure, and area times the change in height is the change in volume. Okay, so we can see the correlation between the work done by an expanding gas and the work done by this man lifting this weight. Okay, and they both go against the gravity, the force of gravity. Okay, let's now consider boiling for a second here. So we've got this alien hanging onto this vessel. The vessel's full of a liquid. It's on a barbecue. The barbecue is a heat source. The change to the liquid's system's energy is dE system. Okay, and as the liquid changes to vapors, it leaves the container, and it does work onto the surrounding atmosphere. It lifts the atmosphere. So PdV is the work done onto the surrounding atmosphere. Okay, this can be a potential energy increase of the atmosphere, or it can be a thermal energy increase of the atmosphere. Either which way, it's an infinitesimal change to the atmosphere's energy, so we don't really notice it. But okay, in terms of the first law, we would write this as dQin, which is heat from the barbecue, plus the system's energy change, dE system, plus the work done on the atmosphere, PdV atmosphere. So before we continue, let's just consider what happens when you heat an expanding system of gas. Okay, for any heated expanding system, you got dQin is equal to the change of the energy of the system, again, plus the work done on the atmosphere. We can imagine that we're heating this gas, okay, and we can express it also in terms of the gas's heat capacity. Okay, so in terms of the number of moles N and the isometric molar heat capacity, we can write dQin is equal NCV dt system plus PdV of the atmosphere. This can be rewritten in terms of the isobaric molar heat capacity, okay, which is on the bottom line. Okay, and it's the same. It's basically you can see that the isobaric molar heat capacity versus the isometric heat capacity differs by the work done. Okay, but they both define the same thing. Now, when a liquid is at its boiling point, the liquid's temperature actually remains constant, okay, because all the energy goes into the latent heat of vaporization, okay? And so dT equals 0, hence the only change to the system's energy is a result of the work done onto the surrounding atmosphere, plus the changes in bonding energy when going from a liquid to a vaporous state, and this is defined by du system. Hence, the latent heat of vaporization, okay, and here I'm defining it as L, and we've got little brackets for liquid going to gas, is equal to the change of the system's energy plus the work done as defined by PdV, which is equal to the change in the bonding energy du system plus the work done again by PdV. So a question now arises, is the work reversible, or can we reverse the work? Now, work is related to the mechanical parameters, those being pressure and volume. Okay, so moreover, in order for system A to do work onto system B, and system B is its neighboring system, then system A must be at a higher pressure than system B. We can also consider system B as something like a car, and system A is a gas tank attached to the car. The tank is high pressure, so you open a valve, and the gas comes out of the tank, and it pushes the car. Again, the pressure in system A has to be greater than the surrounding atmosphere in order to push that car. Okay? For the case of isometric boiling, okay, the change in pressure is 0 because it's isometric. But for the case of boiling at the boiling point, both pressure and temperature are 0. So, okay, now there may be, both of the pressure and temperature may be infinitesimally higher than the surrounding atmosphere, but that allows the gas to do work or to overcome friction of the system. Okay, so we can now ask, is the atmosphere capable of doing work back onto the boiling system? Since the atmosphere and the boiling system are both at the same pressure, consider, can it be done? Again ask, is the atmosphere capable of doing work back onto the boiling system? Since they're both at the same pressure, the answer is no, it cannot. Okay? We can compress a system of gas, but this is us, not the atmosphere doing the work. Okay? So you've got to realize that when the gas expands, it's an irreversible process. Okay? Therefore, work done onto the surrounding atmosphere by boiling and most other expanding systems is irreversible work. So let's consider the implications of lost work. Okay, since work is done onto the atmosphere by expanding systems and it's generally irreversible, we can call it lost work. And you can imagine the atmosphere as a massive body, okay, and therefore as you put energy into it, whether it be work or heat, okay, you do not see a temperature or a pressure increase of the atmosphere. Okay, so that's why we considered isobaric and isothermal in this case. But reality is that the expanding system is doing infinitesimal work onto the atmosphere. Okay, so useful systems are often expanding systems. Okay, so we also now have answers to why perpetual motion is unrealistic. Expanding systems being things like a car engine. You got the gas exploding, or gas-air mixture exploding, and that pushes the piston down in the cylinder, and that actually turns your wheels, right? So the engine is a useful system, and then it's also an expanding system. So perpetual motion in terms of work is unrealistic. Okay, as for the latent heat of vaporization, we can also rate that in terms of work. Okay, the latent heat of a liquid going to a gas is the change of the bonding energy of the system plus the work lost onto the surrounding atmosphere. Does lost work have a sense of direction or directionality? Well, it doesn't matter what direction the system's expansion is, or even if the system expands in all directions. The only direction the atmosphere can be displaced is always upwards. Specifically, you cannot displace the atmosphere into the solid Earth. Equally, if the atmosphere expands horizontally, the Earth's atmosphere's displacement is still limited to being vertical. Hence, lost work has a directionality. Okay. Again, it must be emphasized that such work done onto the atmosphere results in either an infinitesimal potential energy increase of the atmosphere or an infinitesimal temperature increase of the atmosphere. The temperature increase would be from things like molecular dissipation. Okay. It's actually friction between the molecules. Okay. Okay. So the latent heat of condensation. I mean, when a vapor condenses into a liquid, there is an isobaric volume decrease of that vapor, right? Okay, but because it's a volume decrease, the latent heat of condensation does not involve work. If you think about it, it's like removing a volume from the bottom of the atmosphere. All the gases above have to come downwards to fill that volume. And so then the gases, potential energy is converted into kinetic energy, right? So as far as the system goes, there's no work done, right? The latent heat of condensation therefore only involves the bonding energy going from the vaporous/gaseous state to the liquid state, okay? And we write that in the equation below. And this is important because traditional thermodynamics usually just says that the latent heat of condensation is equal to the latent heat of vaporization, and this is wrong. Okay, the problem is we can't readily measure the latent heat of condensation in the same way that we can measure the latent heat of vaporization in an isobaric calorimeter. So anyways, if someone can come up with the experiment, I would love to hear about it. Let's consider the equilibrium condition, and in this case concerning latent heat of vaporization. In equilibrium, as many molecules vaporize as condense. Therefore, there is no net volume change, hence there is no work done onto the surrounding atmosphere, right? Therefore, the energy associated with vaporization equals the negative of the energy associated with condensation, i.e. both are just defined in terms of the bonding energy, i.e. vaporization equals dU and condensation is negative dU. It should be stated that in traditional thermodynamics this is generally explained in terms of isothermal entropy change, and this is a complication of the simple. Equilibrium, whether it be chemical, between states or otherwise, is about the exchange of energy in equaling the energy out. It has nothing to do with entropy. It's all about energy. And we have to stop thinking in terms of entropy. It's a complication of reality. But it is ingrained into the hearts and souls of so many. So we now have a very basic understanding of lost work. It is energy lost into the surrounding atmosphere by expanding systems. We understand now why perpetual motion is unrealistic from a work perspective. What is interesting is perpetual motion is traditionally explained in thermodynamics via this entropy and the second law. And to me, that both entropy and the second law are a complication of reality. Okay? And I'm trying to show a simpler way to envision what we witness. Okay? Now, I'll discuss this in a little more detail in my other video, part 1 and part 2 of expanding systems, and please go and check that out if you care to. So I have a book out, New Thermodynamics, Say No to Entropy, which talks about this in more detail. I'm also rewriting the book for the third time. I'm going to rename it New Thermodynamics, Goodbye to the Second Law. The reason is I had new realizations, and so I had to rewrite chapters 4 and a few other chapters. Okay. Now all the chapters that were rewritten can be found on my website, www.newthermodynamics.com. Most of what is discussed on these videos are in my books, papers, and can be found on my website. Now, it's hard for me because I'm alone at this, so I apologize for my odd mistake, which certainly exists. And as always, I'm really apologizing for being human. Okay, now, people, please help. 2 brains are better than 1. Okay, accordingly, any help and improvement is always appreciated. Okay, I am far from perfect.